Today I am here to give a brief introduction about assemblers. So the flow of my presentation goes like this. I'll tell about what is an assembler and the different types of assembler, the functions performed by each type of assemblers, and what are the data structures used in the design of assemblers, and then I'll conclude the session. So first we'll understand what is an assembler. See, assembler is like a translator which accepts the source program, that is, and generates the object code. So here the source program is assembly level language program. We'll give the input, that is assembly level language program, as a source program, and the assembler generates the object code or the machine code for this. So here assembler, it is like a black box, so we don't know what actually internally it performs the functions to translate the source program into the object code. So the main idea of this presentation is how does this assembler generates the source program into the object code. See, coming to the types of assembler, there are three types of assembler: two-pass assembler, one-pass assembler, and multi-pass assembler. So what actually this pass means? Pass is making a scans over the source input. Here the source input is assembly level language program. So we'll take one by one. So before that, so for that we should know the syntax of assembly level language program. Here I have taken the assembly level language program of SIC machine, that is simplified instructional computer machine. So first we need to know the syntax of assembly level language program. So it consists of three columns. One is the label column, then is the opcode column, this is the operand column. So in the label column, the labels what we are going to use, that should be defined in this. The opcode column consists of the opcodes which we have used to write the program. Then this is the operand field. It consists of the labels and as well as the data values. So now we'll start with the functions of assembler. So fundamental function of an assembler, as I mentioned in the beginning itself, so it accepts the source program, that is, which is written in assembly level language, and generates the object code. So objective is translating the mnemonic operations to their machine language equivalent. So assigning, that means translating means assigning machine addresses to the symbolic labels. So for example, if you consider an example like this, so this is an LDX is a mnemonic and 0 is a label. So we are generating the equivalent of this, the machine code for this LDX and as well as for 0. So in detail, if you take assembler functions, it converts the mnemonic operation codes to their machine language equivalents and convert the operands to their equivalent machine addresses, build the machine instructions into the proper format, convert the data constants to the internal machine representations, and write the object program and assembly listing. So these are the major functions performed by an assembler. So here, before coming to the working principle of different types of principle, first we need to understand the difficulties in designing of an assembler. The main problem is here, it is forward reference. What do you mean by forward reference? Forward reference is a reference to a label that is defined later in the program. So for example, consider this assembly level language program. There is a label field, operator field, that is opcode field, and this is an operand field. In this, so we are assigning, this is the address at which this particular instruction is present. So if you take this STL, it's an opcode, and this is an operand return address. It is referring a symbol which is defined later. So this symbol appearing at the location 1033. So this I call it as forward reference. So if you take, this is forward referencing a label that is defined later in the program. This is called backward reference. This statement is referring a symbol which is defined earlier to this. This is backward reference and this is forward reference. So we'll take one by one 2-pass assembler. So we'll see what all the functions performed by pass 1 and pass 2. 2-pass assembler is the assembler makes the 2 successive scan over the source input. So during pass 1, it assigns addresses to all the statements in the program and saves the values assigned to all the labels for the use in pass 2 and performs some pre-processing of assembler directives. Actual machine code will not be generated in pass 1, only it assigns addresses to all the statements, that's all. And the labels, whatever, some values will be assigned to the labels and also some directives will be processed. That is, here we need to concentrate assembler directives. Assembler directives means for these statement for these mnemonics, machine code will not be generated, only it directs the assembler to do some specific task. So coming to the pass 2, in the pass 2 actually machine code will be generated. It assembles the instruction, that is machine code will be generated, generate the data values defined by byte or word, whatever it is. Perform the processing of assembler then is not done in pass 1. So some directives will be processed in pass 2 and as well as in pass 1. So those who have left in pass 1 so will be processed in pass 2. And the object program and the assembly listing is done in the pass 2. So this is the general syntax of a 2-pass assembler. So for example, if you consider this is pass 1 and pass 2. So we are giving the source program, it's an input to this, and it generates one file called, we'll call it as an intermediate file. So here the actually machine code is not generated, only it is assigned the addresses to all the operands and some labels are processed, and this is given as input to the pass 2 and it makes once again scan over this input and it generates the object file. So here some important things I have mentioned you need to observe here. It is opcode table or symbol table or something like this. So let us understand what actually these things are. So now see, while designing an assembler, some important data structures we need. The important data structures are opcode table, symbol table and location counter. So what is this op table? Op table, it is a database which consists of all the machine code supported by that processor and its equivalent machine code will be stored in that opcode table. What is the symbol table? Symbol table is one which is generated during pass 1. So you can observe here it is the pass 1, it is referring opcode table, this is a predefined database, and this is symbol table which is generated by pass 1. So it searches for all the labels and those labels placed in the symbol table and it assigns the addresses to all the labels or the symbols during pass 1, that is symbol table. Next is the location counter. It is like a program counter. The program counter is one which points to the next instruction to be executed. So here the location counter here is the one which addresses or it points to the next statement to be assembled. So there's a difference between here the location counter and the program counter. Program counter, it shows, that means it holds the address of the next instruction to be executed. Here it is to be assembled. So these are the contents of the opcode table. So mnemonic and its machine code. Characteristics, it's a static table. So the implementation, how you to implement all these things, we can go for a array or hash table, easy for search. Next is the symbol table. What are its contents, characteristics and implementation mentioned here. And see, this is one simple program I have taken. For this, these are the symbols which we are encountering in that assembly level language program, and these are the addresses we have assigned to those labels. So then what actually the object program consists of? There are three major records are there: header record and text record and end record, and every object program is having its own syntax. That syntax follows like this. It consists of three types of records: header record, text record and end record. Next is one pass assembler. Next I'll move on to the second type, that is one pass assembler. Here we'll make only one scan over the source input. The main difficulty here it is handling of forward reference. So that is the data items which appears later part of the program, how to handle this. So the solution here it is, so data items. So what solution we can think of is, we can enforce the programmer to define all the symbols before it encounters. It's not a good practice and it's not a good solution. So there are two types of one pass assemblers. One is load and go, and the other is the produces the usual kind of object code for the later execution. So then we'll take up the load and go assembler. So load and go assembler, these are the some of the characteristics of this. Normally it is useful for program development and testing, and it avoids the overhead of writing the object program out and reading it back. Both one pass and two pass can be designed as a load go. However, one pass also avoids the overhead of an additional pass over the source program. For a load and go assembler, the actual address must be known at assembly time. We can use the absolute program. So the name itself suggests that it is load and go assembler. Here is an intermediate file will not be generated. See, assembler also sits in the main memory. Assembly level language program also sits in the main memory. So assembler just takes the statements from the main memory and also generates the object file, and directly it places the object file onto the main memory. So forward referencing in one pass assembler. So here for any symbol that has not been defined, here it is. So what actually here it is, so it omits the address if any statement, if it encounters a symbol which is a forward referencing symbol, it omits that and insert the symbol into the symbol table with the mark it is undefined, and whenever it is referred, so immediately that that means here and this is encountered, the proper address for the symbol is then inserted into any instruction previously generated according to the forward reference list. At the end of the program, any symbol table entries are still marked which indicate that it is an undefined symbol. So search symbol table for symbol named in the end statement and jump to the location to begin the actual execution. So actual address, that means starting address, must be specified at the assembly time. Producing an object code. When external working storage devices are not available or too slow, then between the two passes, that is when that means here it is the definition of symbol is encountered, the assembler must generate. Okay. The loader is used to complete forward reference and could not be handled. So we'll further discussion on what is that and multi-pass assemblers I'll continue in the further discussion.